So now we're going to discuss solubility equilibria. So this is an extension of the equilibrium processes that we have been talking about in chapter 13 and also chapter 14. So in chapter 13, we talked about just equilibrium in general, and we applied it to homogeneous and heterogeneous systems. Now, solubility equilibria are actually heterogeneous systems, and we're going to see how that works in a second. But the first thing that I want to do is point out that these solubility equilibria occur when the dissolution of a compound and the precipitation of it happen at equal rates. So let's go ahead and write that down. So solubility equilibria occur when the dissolution of a compound and the precipitation of the same compound happen at equal rates. So the bottom line here is that the compound is dissolving in solution, and then it's in the forward direction, and then it's also precipitating in the back direction, and those are happening at equal rates. So just another little recall. So this is from Gen Chem 1. Remember the discussion about solubility. And remember that we had a solubility table. And on that table, we said certain things were either insoluble or soluble. And you had rules to kind of predict what that was. And basically what we were talking about, but we didn't specifically really say, is that the solubility of a given substance can vary from essentially none to infinity. So let's go ahead and write that down. So the solubility of a substance can vary from essentially zero to infinity. Now, the reason why I say essentially zero is because it's not ever literally zero, okay? It might have an extremely small KSP or solubility product, which we're going to talk about in a second, but there will be even a tiny amount soluble. So we learned a couple of terms. So insoluble, okay, we saw that. Another one that's related is sparingly soluble. And those are often kind of lumped together. So sparingly soluble is just going to mean just a little bit more dissolves than the actual insoluble compound, which essentially none dissolves because it's such a small amount. But either way, often with these, we're going to see this type of problem related to a solubility product. So these insoluble or sparingly soluble compounds are going to have a KSP attached that we're going to be able to use to determine just how much does dissolve. So now miscible, that says that the compound is very soluble. And often we're not going to use a KSP with those types of problems because the KSP would actually be very large. So a solute that does have this finite solubility, so a certain amount of it dissolves, can yield a saturated solution. So that's something that you've heard of, a saturated solution, and that's basically where you've dissolved all of the compound that you possibly can in that solution. So a solute with some finite solubility yields a saturated solution when it is added to a solvent in an amount that exceeds its solubility. So when we discussed saturated solutions in chapter 11, that's what we were basically talking about, is that we've added enough of this compound or this solute to the solution that we've exceeded its solubility. And so we now have a saturated solution. And so the result of this is going to be a heterogeneous mixture of this dissolved solute, which is the solution, and the undissolved solute at the bottom of the flask. So the result, a heterogeneous mixture of dissolved solute, let me fix that, dissolved solute, and that's going to be the solution, and undissolved solid, at the bottom of the flask or the beaker or whatever you have. Okay. So that's what we're going to have. So let me just draw a picture of that. So we're going to use silver chloride as an example. So here's our resulting solution. Here's the silver chloride at the bottom of the container. And then up in the solution, we're going to have lots of ions floating around. Okay, so I'm not going to draw them all in, obviously. That would be quite the interesting drawing there. And so let's go ahead and just write the equation for this, the equilibrium equation that we're going to be looking at. And that's this silver chloride. In the forward direction, we're going to have dissolution. In the backward direction, we're going to have precipitation. And here are our ions in solution. Okay. Now, we can write an equilibrium constant for this reaction just like we did in chapter 13, except for now we're just going to give it a new name. And so the equilibrium constant for solubility equilibria is KSP. So if we're talking about solubility equilibria in particular, we're going to use KSP, and that's the solubility product constant. Okay. And so let's go ahead and write out the expression for that. So if we're going to write out the equilibrium constant expression, or the solubility product constant expression, then we're going to just go up to our equilibrium expression up here. We notice the coefficient is 1 for silver and silver ions, and also for the chloride anions. And so I'm not going to put that there explicitly, but the power here is 1. So I put it there, but I'm going to erase it. Okay. And so that's assumed. And so this is the solubility product constant expression. Now notice that the solid is not in the equation. And so think back to heterogeneous equilibrium expressions. And remember that the solid does not affect the equilibrium established. So remember, we can add more solid to a heterogeneous equilibrium, a system that's at equilibrium, and it doesn't affect the equilibrium. Okay, so I'm just going to write down, notice the solid is not in the equation. Does not affect equilibrium. Okay, so go back to chapter 13 if you have forgotten that, because that's something that you're going to want to refresh for yourself, because we're going to use that, and we're also going to use Q. You're going to see that too. So you want to go back to chapter 13 for that also, if you forgot. Let's look at another example. Let's look at calcium carbonate. And we're going to write out the expression. So calcium 2 plus and carbonate anions. So if you've forgotten your polyatomics, go back and get those too. And we want to write the expression for the solubility product constant, KSP, for this also. You're going to see it's just really easy because we're going to go up here to our expression. We see the coefficient is 1. So the power is going to be 1 for both of these. And there it is.